Thank you for joining this session. So some of you might have heard about Storage Performance Development Kit in one context or another. But as title suggests, this context is infrastructure offload. I'm Tomasz Zawadzki, and together with Jacek Kalwas, we'd like to go through what problem infrastructure offload solves, how it addresses it, and then go into detail how SPDK fits into that. So first of all, let's try to level set what problems there can be with managing the infrastructure and how it can possibly be addressed. So as you might imagine, configuring a single host versus multiple vastly different hosts can be a problem of scale. Together with that, software running on the host and the infrastructure, software running on the host configures the infrastructure and thus has some split responsibilities between what's provided to the host, to the application, as well as to the infrastructure. So another problem that might arise is addition of new features, which often requires changes in software and most likely hardware as well. This is even multiplied when considering offloading different types of workloads. So going back to the issue of scale, doing that dynamically across the whole data center is the problem that infrastructure processing unit tries to solve. So this is where IPU comes in. This is in general an PCI card that's inserted into the host. The IPU presents devices like NVMe to the host and thus allows the host to interact directly with the final device rather than with the infrastructure, thus separating infrastructure and the tenant. This allows for a separation between those layers, as well as improve system level security, as that's all moved down to the IPU, and allows for easier management and control of the infrastructure on the data center level, not interfering with the hosts themselves. So as you might see on the left, this is an example diagram of the Mount Evans board and some of its features outlined over here. But features of the IPUs differ from generation to generation, from the one company to the other. So IPUs in general allow for dynamic changes of what's presented to the host and what features there are offered, allowing to both limit and expand the host capabilities just by using the IPU. In context of storage, the IPU could either present the storage as a target or consume it as an initiator. And the later case is what will be the focus of this presentation. Let's go over what kind of storage use cases where the IPU is used as initiator there can be. So the description of this slide addresses the issues that were described in the problem statement itself. So first of all, in this specific use case, only the NVMe driver is needed on the host. This component, NVMe driver, is available on any modern system, be it Linux, Windows, or anything in between. Normal PCI devices can be consumed immediately with no setup required for for example, for the NVMe-oF. And thus, there is no need to run the initiator on the host. There is no need to orchestrate it and so on that layer. And on a similar note, all the interesting things happen exactly on the layer of IPU, connecting to the remote target, handling the NVMe-oF discovery, or the support for multipath. All happens down on the IPU. So next case is similar, but pretty different, is that in here, the NVMe driver exists in the VMs rather than the host. And thanks to support for multiple virtual functions, it's possible to pass the VF directly to the VM. For cases where VMs are in use, this allows for implementation of interesting features like live migration, coordinating hypervisor on the host, as well as the IPU. More on that in Jacek's part. By now, you probably can see the trend. This presentation will be focused on NVMe, but there are other types of host interfaces that can be presented to the host. Here, here, a device such as VirtualBlock can be passed directly to the VM, and this requires a different component to be used on the IPU, such as Virtual Target. Note that this change is completely transparent from host point of view. No matter what kind of target is used on the IPU side, it's still there's very little configuration to be done on the host side. Here, in latest SPDK, an abstraction to implement different virtual block transports was added to allow others to write their own transport to expand these capabilities. And last but not least is not really a use case, but more of a build-up on previous usages. The storage application can be configured and customized to suit the required use case without changes to the hardware. Different devices can be presented to the host, of course, as mentioned. But those devices do not need to map one-to-one to those on the remote NVMe-oF target. Instead, those could be, for example, split using logical volumes or offer additional capabilities like crypto, compress, caching, or many others. This is where Accelerator framework comes in. It can be used to offload operations from such BDEFs or from the target or initiator side on the IPU. So let's go. This completes the overview of the storage use cases, but let me talk briefly on projects that allow all of this to be put in action. Starting off with the infrastructure programmer development kit. So IPDK is an open source framework that allows for infrastructure programming. Storage is but one of the use cases within broader spectrum of possibilities for it. Please drop by ipdk.io to learn more. Finally, switching to the storage performance development kit. So SPDK is a set of user space libraries, drivers, applications, and tools for storage solutions. A community-driven BSD license project. So the whole stack and each of its components is optimized for bleeding-edge storage solutions. Today, we are going over a few specific ones, but please note that the architecture based on composable blocks is what allowed to piece together the infrastructure offload in SPDK. So first, at the bottom, we have the NVMe driver used as NVMe-oF initiator, and one layer up is the NVMe BDEF that presents the device as a generic block device. Second, there are various parts of the accelerator framework that enable offloading operations performed by the block devices or driver and targets. Finally, the target protocols where NVMe-oF and its transports will be the chief part of the discussion today. If you'd like to learn more on those or other components of SPDK, feel free to go to spdk.io and catch us on Slack or mailing list. One call that needed to be made here is for Storage Management Agent, in short SMA. This is a service running on the IPU managing SPDK application. By design, it is intended to be generic enough to work with any orchestration framework. And as an example, during development, a key way for us to prove out the design was to make sure it aligns with Kubernetes CSI APIs. So SMA is a very fresh addition to SPDK, currently supporting API to present NVMe or virtual block devices to the host, and connections to remote NVMe volumes. Let's get to the fun part. So SPDK had support for NVMe for quite a while. The part that is novel is the context of the IPU and how to present NVMe device to the host from an IPU, no matter what kind of device it is actually backed by. Quite a while ago, the NVMe 2.0 spec recognized the PCI as just another transport alongside TCP, RDMA, or fiber channel. This basically follows the organization of the components already done in implementations like Linux kernel or SPDK. The interesting part happens when two observations are made. SPDK NVMe target already fully emulates an NVMe device based on any type of SPDK BDEF, and transports themselves are pluggable, allowing for additions of the new ones. Combining those two to present any type of BDEF to the NVMe PCI driver, serving as an initiator on the host. So here, I'd like to hand off to Jacek to describe such new NVMe transport and all the advantages and challenges that come with it.
Thank you, Tomasz. That is a great background for what will follow just next. So let's proceed to the another slide, which is NVMe Protocol Interface Transport, in short NPI. This transport inherits its name from one of the hardware modules on the Intel's IPU. And NPI Transport is yet another transport which can fit into SPDK NVMe framework. Here, NPI Transport, I want to mention that it was developed for the purposes of this IPU called Mount Evans. I want to mention that it is a vendor-specific plugin which acts as a glue between IPU components and SPDK libraries, and eventually those allows to reach remote storage. And it was initially designed just as a validation vehicle for IPU components, but now as it covers defined storage use cases, also described today, and shows more value, it tends to get into production. SPDK is a great choice for IPU storage software stack implementation, as it is already widely adapted for high-performance solutions. And with open source and user space nature, it favors fast cadence of customization and innovation. Although the plugin itself is vendor specific, Low-level details are encapsulated by corresponding drivers within with well-defined set of APIs. Some design concepts might be generic enough to be leveraged by different IPU implementations. And with that, let's dive more into technical details, treating NPI Transport as an example of IPU plugin to SPDK NVMe-oF framework. So with next slides, we'll cover some design details, potential solutions, and challenges. External management entities can dynamically configure SPDK storage application using JSON RPC protocol. Most of the JSON RPC methods are inherited from SPDK BDEF and NVMe-oF layer and can be used as is. And the important ones are being listed. These are NVMe-oF create subsystem, which constructs NVMe-oF target subsystem, BDEF NVMe attach controller, which constructs NVMe BDEF and can be also used to enable multipath. And there is NVMe-oF subsystem add namespace, which allows to associate BDEF with the subsystem. Other methods are also already defined and capable to cover extensions required by specific transports. And these are NVMe-oF create transport, which constructs NVMe-oF transport, in this case of NPI type, and NVMe-oF subsystem add listener, which constructs listener, which we'll refer later to as endpoint. During transport create, IPU specific device exposed to user space is getting attached. And over time, SPDK ENV library was adjusted to allow that. Driver with fields like PCIe class or device ID needs to be registered using simple macro, and SPDK PCIe enumerate function does the rest. IPU specific options can be provided as required for IPU components initialization and to enable disable some subset of the features. And design is simple. It is a JSON value object which is getting passed to the transport layer, and any extra options can be parsed there. It was not designed like that from the beginning. Some changes were required on generic NVMe-oF layer to achieve that. Interface with such capability fits well to define global settings, which doesn't require runtime changes. I want to mention that as a part of transport create, also poll groups are getting created. These are entities which groups cupers and allows to process commands within single thread. Endpoint object. This refers to the another method which we listed here, is associated with given subsystem which can contain namespaces, and address specified defines mapping to function exposed on the Xeon host. Later, when events or commands arriving from function exposed on the host, then lookup for corresponding endpoint is required. During NVMe controller initialization, endpoint object coordinates NVMe controller object creation. This will be covered later. Some of the resources are tightly coupled with given function exposed. So similar mechanism to provide additional transport specific configuration also fits here. Design approach described helps with isolation and management. And all interfaces are already well documented. You can find more info under given link. SPDK is flexible enough to allow for easy extensions with custom configuration. And just as an example, there could be a method to limit minimum or maximum bandwidth per function. And interesting part is that most of this configuration just described, the methods are simplified and abstracted with SMA interfaces. And on few we still need to work on. When this is the next slide, on which we'll cover request state machine. So when commands are fetched, they are being associated with what is named as NVMe-oF request. Regardless of the transport type, request processing state machine is similar. Usually, a poll group has some pre-allocated requests available. And again, for allocation efficiency and to not share with other groups the resources, threads, I mean, to not share resources on different threads, we have these pools, and this would not enforce to have any synchronization. So we have to keep in mind performance at the first place. New state is kicked off when the NVMe command is fetched and associated with the request object. Most of the commands require to allocate data buffer, and there is a list of pre-allocated buffers per NVMe-oF poll group, which can be obtained using existing APIs in NVMe-oF layer. This is NVMe-oF request buffer interface. And for transfer states, it is required to move data payload from one memory domain to another. And regarding that, we'll cover more details later. Request object is passed through to SPDK NVMe-oF layer for further processing in execute state. And the interesting fact about this function is when the subsystem is not active, then requests are getting queued. This is happening, by example, when namespaces are getting added or live migration is happening. Internally, there is a check if given command shall be processed as fabric, admin, or IO command. Fabric commands corresponds to what NVMe spec defines as connect and set or get properties. Those are not defined for memory-based transport types, but still required for NVMe emulation. I will refer to these operations as internal communication, and this allows to create or configure NVMe controller. As for admin commands, almost all, if not all, commands like identify controller or get log page are also fully implemented internally by SPDK NVMe layer. Also, a bunch of helpful NVMe spec constraints as part of validation checks are already implemented there. IO commands path is the one which essentially passes through the commands for further processing to BDEF layer. At the time command is processed, transport is notified about that via complete function registered into NVMe framework. Its execution will advance the state and eventually free associated resources and request object itself as the last step. As for SPDK v22.05 release, there are 11 lines of code, whereas NPI Transport is 7K. In case of that, NVMe emulation engine not leveraged, most of the logic would need to be embedded into IPU-specific code itself. For sure, there are some options to move logic into NVMe generic layer later. Here we'll cover controller state machine, and focus will be put into initialization flow as an example to highlight the design and potential challenges. Function on the host starts a procedure of the controller initialization, and NPI Transport is getting notification about that. NVMe cupers are getting registered to NVMe poll groups, and you can think of NVMe cupers as virtual channels responsible to carry commands. And that is followed by connection of admin NVMe cuper. On this call, NVMe controller is being created. After such object is created, it shall be the NVMe layer should be capable of handling properties set. With that, controller is getting enabled and ready for following connect commands. Number of connections being done corresponds to poll groups created. And please notice that in comparison to TCP or RDMA transport, this is fully internal operation. There is no communication with an external host here. After all NVMe cupers are connected, NPI Transport can advertise to host software that controller, which is being emulated, is ready. Host software proceeds with initialization with admin commands submission. NVMe framework was extended in the way that specific transport, in this case NPI Transport, can override some of the default settings like optional NVMe command support or asynchronous event request limit during identifying the controller. Interesting fact is that number of the host NVMe cupers doesn't need to match NVMe cupers, as it just doesn't scale. The implication is that some of the NVMe commands needs to be terminated and handled on the NPI Transport layer. And the example of such commands are set features with number of queues or create NVMe IO queues. Okay, the next slide is about data transfer, and it is important step in the request processing. It is required to move and access memory from one domain, which is host, to another, which is an IPU. NPI Transport, in this case, is responsible to initiate that data transfer. Separate DMA instance per NVMe poll group is a key to avoid synchronization. And again, we need to have a performance in mind. So that is the reason. As NVMe layer doesn't support PRP conversion, it needs to happen on NPI Transport layer. Depending on the configuration, this DMA operation can be chained with CRC calculation. It is done by LC Krypton compression engine, and NPI Transport can use that chain operation to support diff-dix, which are commonly used integrity protection solutions for storage. The main difference between diff and dix is where metadata protection information is placed. And there are also few CRC algorithms available for diff-tix usages. As for the security and data encryption, LC also allows to offload XTS-ES operation. This chain operations allows to reduce memory bandwidth utilization and latency. There are a bunch of resources which are specific to IPU capabilities, and those can be handled differently. For example, allocation policy can be driven by orchestration layer, like number of queues for given function can be specified during endpoint creation with NVMe-oF subsystem out-listener method, which we discussed. And next, internally allocated from the available pool of resources, which size is strictly related to the IPU capabilities. Another way could be to define some default policy which would allow to distribute queues equally among available host functions, which essentially leaves the configuration mentioned as optional. Some of the resources we already covered, like requests, which are being associated with the commands. And this can be pre-allocated and distributed among available pool groups to form private list of resources. Another important resource is a namespace. Those are tricky because we want them to dynamically add or remove. In the NVMe layer, there was a design change to provide notification to the transport layer. With that, specific IPU transport can validate namespace attributes against supported capabilities before it is successfully getting added to the NVMe subsystem and presented to the host software. I assume that number of the namespaces supported or other resources can be also limited in number for given IPU implementations. To keep track of allocations from some specific set, SPDK bit array works very well. Resources like encrypt, decrypt keys, and possibly others require custom JSON RPC methods. How to deliver and store it in a secure way is IPU implementation specific. And we can go to the next slide, which is the quality of service. So IPU commands in flight are limited in number to match requirements for low latency, and there are IPU specific methods to configure commands precisely for each function. Limiting commands per function allows to achieve isolation between functions, which is one of the mechanisms to protect against malicious VMs. Maximum bandwidth and IOPS capability of IPU is limited itself and needs to be carefully managed by orchestration to meet service level agreements. For that, also custom methods are getting defined. Bandwidth and IOPS limiting per function is also supported by IPU hardware, as opposed to software solution for setting limits per namespace. This can potentially impact performance. This quality service settings can be changed dynamically. And the next slide is about the live migration. And I will start with the statement that live migration is important use case required by CSPs. And the focus here will be put on high-level interactions between IPU components. Other components involved, like hypervisor on the host and orchestration frameworks, are out of scope for this presentation. So SMA coordinates saving configuration and states between SPDK NVMe-oF layer and IPU components. At some point, there is a request from orchestration to initiate safe migration flow. SMA can query existing endpoints and its configuration using NVMe subsystem getListener method. Transport-specific options provided during endpoint creation are also being dumped in JSON format, as there is transport hook registered to allow that. Also, method allows to specify subsystem NQN matching to reduce output and removes burden of filtering the data. NPI Transport currently defines custom JSON RPC method to cover safe flow. As the very first step, it kicks off the function to pause NVMe subsystem. It simplifies the procedure in the way that outstanding IO commands are being completed, so there is no need to migrate those. Only when the subsystem is confirmed to be in pause states, we can proceed to the next operation, which is NVMe controller safe migration data function. It does a lot of useful things, like saving the controller features configuration or register values. Moreover, it saves information about outstanding asynchronous event requests. And these are the only commands we want to migrate, because the procedure shall be seamless for the software stack running in the VM being migrated. Be aware that there is a complementary function which allows to restore NVMe controller migration state. Next, some configuration and states like queues, attributes needs to be saved, and this is being done as a set of calls to underlying NPI driver used within NPI Transport. With NVMe get subsystems, it can be verified what namespaces are currently attached, and with bdef get bdefs, required attributes, detailed attributes, can be queried. It is important that orchestration, which initiates migration, is also not modifying the state at the time migration is being done. By example, with adding or removing namespaces, as that would result in inconsistent state of destination system compared to what was there in the source system before migration happened. SMA, having all this data, can proceed with the flow further. Saying that, I'm passing presentation back to Tomek. Thanks.
Thank you, Jacek. So after hearing all the things that NPI does, you might be wondering, what else is there to do? So here are some areas of interest that SPDK and IPUs might see changes in. So we've talked extensively about changes in NVMe target, but there are still opportunities to offload the NVMe initiator too. So next point is motivated by high availability needs of solutions such as IPU, and possible changes might include ones helping with live upgrades of the SPDK storage application. Accelerator framework is area of very dynamic development in SPDK recently, and seeing as the different IPUs offer vastly different feature sets, this acceleration framework will become increasingly important. And finally, during this talk, we've focused on storage backed by NVMe over fabrics. But thanks to BDEF layer offering the required separation, this could be replaced with any other type of packets. So summing up, if there are a few things we would like you to walk away from this presentation with, those would be: the infrastructure processing units allow for flexibility and performance in evolving data center, and that the SPDK NVMe-oF target serves as an ideal NVMe device emulation for IPU. There are some opens that we hope to see change in the future, such as upstreaming of the NPI Transport, finishing the changes in SPDK NVMe-oF interface to support live migration, and the extension of the SPDK accelerator framework for use cases like IPU. Thank you everyone for joining the session. Please join us at spdk.io. We'd love to hear your feedback.